Now we're going to use what we've learned about shape and geometry to decide if a molecule is polar or not. So dipole moment means that a molecule has a positive end and a negative end. It's caused by polar bonds, and it also has to do with the shape. The shape has to be not symmetric, asymmetric. Okay, let's remember what a polar bond is. So this bond here, oxygen to hydrogen, is very polar. And the reason that it's polar is because oxygen has a stronger pull for electrons. We would say oxygen is more electronegative than hydrogen. And that means that these two electrons are being shared are literally spending more time with the oxygen than with the hydrogen. So that's why I have this little symbol here, meaning that this oxygen has a partial negative charge. It's not like a -1 charge, but it is a partial negative charge. Same with hydrogen. It has one proton, but the two electrons are spending more time over here, so it's kind of exposed, we would say. It has a partial positive charge. So this molecule has two polar bonds, and then also it has these lone pairs, and lone pairs contribute to the dipole moment as well, in fact quite a bit. So I'll show you how we draw this. So this is a polar bond. We draw an arrow. The arrow starts at the positive end and points toward the electronegative or the more negative end. Okay. The thing is, we really could do the same thing here, that these electrons are out to that end in a way. We don't usually do that with the lone pairs, but anyway, if we were to look at the molecule overall, if we know this shape, it's tetrahedral, the net pull for electrons, or the electron-rich part of the molecule, is essentially kind of pointed down this way, where this end of the molecule, like this end, is positive, and this end is very negative, maybe including that oxygen is more negative. So because it has a positive end and a negative end, this is a polar molecule. We would say that this molecule, well, I got kind of messy there, this molecule has a dipole moment. Dipole moment usually kind of means is a measure of the degree of charge separation. I mean, the simple way is it has to do with how polar the molecule is, but anyway, so this is a polar molecule. Let's look at another thing that can happen if you have polar bonds. Sometimes you have polar bonds that kind of cancel. So this oxygen is more electronegative, so this definitely has a polar bond going out each way, but they're kind of opposite. You can think of it as they cancel. It doesn't have like a positive end and a negative end, so we say this has no and so this is a non-polar molecule. Again, this is kind of a little bit of a strange thing because you have polar bonds, but because they're oriented opposite each other, they kind of cancel, so the molecule as a whole is non-polar. Well, this idea of them canceling will occur every time you have the same atom attached on every electron group. In other words, so this is the one we just saw. The linear has no dipole moment. If we have a trigonal planar, it has no dipole moment, and so we're talking about it has an atom in each of the 3 places. Those will kind of cancel each other as well. And same thing here. Anyway, and so you can kind of tell, we actually have not talked about square planar yet, but anyway, they do cancel even if they're not like straight across from each other. Let's look at this example. These are both tetrahedral molecules, and let's see what we think about which one would be polar. Chlorine is more electronegative, so we have polarity pointing toward those. But they're kind of in opposite directions to the corners of the tetrahedron. On this molecule, we have 3 that are polar, but this top bond is nonpolar. Okay, and so that means that the net polarity here is going to be straight down. Okay, so this molecule is polar. This molecule is nonpolar. Another thing we want to introduce before we do some more examples, and we'll look at both polarity and isomers with them. So we're looking at isomers now. Isomers, they're compounds that have the same atoms, but they're connected in a different way. So they have the same atoms, but the atoms are connected differently. In other words, they have a different skeleton. And we're going to see these with the carbon compounds. Like I said, we're doing a few simple carbon compounds, and you'll kind of learn what the different isomers look like. But anyway, sometimes people confuse this with resonance because we'll draw more than one structure. And anyway, I'll help you decide the difference between those. So isomerism means having isomers. Okay, I think we're ready to practice some examples.